circuit there is a capacitor as an energy storage element, and a transient behavior is induced by the closing of a switch in the circuit at time equals 0. There's a 3 ampere current source initially connected to the circuit, and that is effectively removed when that switch closes. So we're looking at the output voltage V sub O for this circuit, which happens to be the same as the capacitor voltage V sub C, and we might have to consider the capacitor current I sub C. So we'll proceed using the step-by-step approach to solving this first-order transient problem. So the first step is to assume that the form of the solution for the VO of t will be K1 plus K2 e to the minus t divided by tau, time constant. And we are going to, in the next steps, determine the values of K1, K2, and that time constant. The second step in the step-by-step approach is to consider the time t equals 0 minus. This is just before that switch closes, and we're going to want to determine the variable VO voltage at V equals 0 minus. This is a steady state condition, and therefore the capacitor current IC at 0 minus is equal to 0. We'll do a KVL summation. We'll do a KVL voltage summation around the path indicated here. We'll do a KVL summation around. We'll do a KVL summation around this closed loop, and we'll have that VO at 0 minus is equal to the 2 VA dependent source plus 24 volts from the independent source, and that labeled voltage V sub A, which controls a dependent source. And we recognize that the VA at 0 minus is caused by the 3 ampere source flowing through that 4 ohm resistor. So this would be 4 ohms times 3 amps is equal to 12 volts. Thus the VO at 0 minus will equal 2 times 12 volts plus 24 volts plus 12 volts, and that is equal to 60 volts. So that's our initial condition for the voltage V sub O. This also is the same as the capacitor voltage VO. This is also the same as the capacitor voltage at time 0 minus. Next step 3 will be to consider the time t equals 0 plus. Now the switch is closed, effectively disconnecting the 3 ampere source from the circuit. We have a capacitor current, possibly a capacitor voltage, both at this 0 plus time. So we'll use the concept that VO at 0 minus is equal to the capacitor voltage at 0 minus, which will be, by continuity of that capacitor voltage, the capacitor voltage at 0 plus, and that is equal to our variable V sub O at 0 plus. So we can say therefore VO at 0 plus is just what we discovered in the previous step, 60 volts. Step 4 is to consider the circuit behavior as time goes to infinity. We'll do a KVL again and recognize that the capacitor current is equal to 0 because we're in a steady state condition as time goes to infinity. So therefore we can say that there's no voltage drop across the resistors in the circuit. We actually have two resistors in parallel, but there's no current flow, no voltage drop, so VA is equal to 0. And we have that VC and thus we have VO of infinity is equal to 2VA plus 24 volts plus VA, but we said that the VA is 0, those cancel out, and the VO of infinity is equal to 24 volts. Now in the step 5 of the step-by-step approach, we have to determine the time constant for the circuit. The time constant will be R Thevenin times the capacitance value, and we have to determine that Thevenin resistance seen by the capacitor in the circuit. So we'll draw the effective circuit for t greater than 0. Again, we have those two 4-ohm resistors appearing in parallel. We'll draw the equivalent circuit for t greater than 0. We have those two 4-ohm resistors appearing in parallel. We have the 24-volt source, our dependent source, 2VA, and then the terminals where the capacitor is connected. So we want to determine the R Thevenin looking into this circuit. This is complicated by the fact that we have that dependent source 2VA in there, where V sub A is defined as the voltage across these two resistors in parallel. So the way we can handle this is we set the independent source to 0 and connect a test current, essentially connecting an ohm meter to this circuit. Call the value of that I sub x. We'll calculate the voltage V sub x, which appears across the terminals, and the R Thevenin will be the ratio of V sub x to the test current I sub x. V sub A will equal V sub A will equal, we have V sub A will equal V sub A will equal 4 ohms in parallel with 4 ohms times our test current I sub x, which flows around that loop. And this is equal to 2IX for the two 4 ohms in parallel form a 2 ohm equivalent resistance. Now we can do a KVL around the entire loop as we've done several times before. We have V sub x is equal to the 2VA plus VA is equal to 3VA, and that's equal to 3 times 2IX, which is equal to 6IX. Remember that 24 volt source is set to 0 in this Thevenin resistance determination. So we have V sub x is equal to 6IX. R Thevenin is the ratio of Vx to Ix. That's equal to 6Ix divided by the Ix is equal to 6 ohms. And then we can say the time constant is equal to R Thevenin C is equal to 6 ohms times 2 farads for the capacitance, and that's equal to 12 seconds. Now the final step here is to put the preceding parts together, and we have our assumed solution VO of t is equal to K1 plus K2 e to the minus t over tau. VO at 0 plus will be the sum of the coefficients K1 plus K2, and that's equal to 60 volts. And VO, as time goes to infinity, is just equal to the K1 coefficient, and we determined that was 24 volts. And we can solve this for the K2 coefficient being 36 volts. So we can say VO, so we can then say VO of t is equal to 24 volts for the K1 plus K2, which is 60 E. So then our final form of the VO of t will be equal to K1, which is 24 plus 60 e to the minus t over 12 seconds for the time constant volts, and this applies for the time t greater than 0.